This is lab number 6. In this lab, we're going to be watching a cutting tool moving very slowly across 3 different materials: aluminum, brass, and copper. This sort of simulates what goes on in a cutting process, like what you saw in lab number 4, but because we've slowed it down, we can carefully see the formation of the chip. In this lab, we're going to be varying the speed at which we're feeding, so the table feed is going to be varied, and we're going to stay with a consistent depth of cut as we go across our 3 different materials. As we do this, we're going to be measuring both the horizontal and the vertical force, and then once it's produced a chip off of each material, we're going to measure that chip thickness. In lecture, we talk about the different forces that take place at the point of this cutting tool. So here we're going to do this in a practical application. So Dominique's going to give you a little overview of how the lab runs from a practical standpoint.
Okay, so over here we have the app that's going to actually record the data, so the TracerDAQ Pro app. Once you open it, let me actually open from the start just so you see. So once you open it, it gives you a few options whenever it actually opens.
Yep.
Okay, and you just press run and you should come up with this screen. So what it's collecting data from are these amplifiers that record both the horizontal and the vertical forces. So this will save it as a .csv file that you will get to run your analysis on. So that's it for over here. On the machine itself, the depth of cut is always 0.004 of an inch, and if you come this side, this is the wheel that dictates the depth of cut. Here I've already set it for our first cut, so we don't have to do anything for that. But each line or each little line on the wheel, indicates like 1/1000 of an inch. So we just have to move it 4 tick marks. All right. So feed rate. Feed rate is determined or is set over here. So the first feed rate we have is 0.6. So how we set 0.6? So first we bring it down. 0.6 is up here. So we want to bring it all the way over here. So as you see, there's 3 numbers here, and this second tool, this second handle has 3 clicks. So since 0.6 is the first one up here, you want to move it on this, like this, at this indent, but also the furthest one up. So that is our first feed rate. And so to just start that, then we have the camera actually, so we can see the zoomed in version of what's going on over there, just to keep track. So now we're just going to start recording the data. So Jesse, I'm going to need you to press play over here. Yes. All right. So now, so now the piece is moving, the cut has started. So this is 0.6 inches per minute. So obviously it's going to be quite slow, and we're going to be here for a while. But right now it's cutting through the aluminium.
You can see the chip forming at the point of that tool. We see it forming here.
It looks big, but if you bring it over here, you'll see it's just a really, really tiny piece. I don't know if you can even see it. No. But trust me, even without the camera, it's hard enough to see. So we'll be here for a bit. So you want the piece, so you want it to finish cutting through the aluminum and stop it, so that you can record that and save that data as aluminum, like 0.6.
What is being recorded on the computer is both the horizontal and the vertical force. You don't see much moving on that screen because it's a pretty constant force. When it reaches the end of the piece of material, we'll actually see this drop off. Right now, our chip, we're about
Press play.
2/3 across.
You didn't press play. It's not recording anything.
So we see here that our chip is now curled over and it's going to curve underneath itself. We're maybe 3/4 of the way across our piece of aluminum, so you can see that we're moving pretty slowly here. So now, when we reach the end, the trick is catching this chip with the tweezers before it falls and we can't find it.
There you go. And we are done with that. So that's our whole chip right there. And so we're going to be using a micrometer to measure the thickness of that chip.
Okay, so we need to measure our chip thickness here. So Jesse has broken the chip into a manageable piece and is putting it in our digital micrometer. This is going to be the chip thickness for aluminum, table feed of 0.6.
0.01375.
Cut. I'm going to speak first, so don't hit any buttons yet. Now we are going to do our brass piece of material.
Okay, so it's at the same feed rate, so 0.6, and again we just go. Again, as you see, it's moving extremely slowly. The camera fools you into thinking it's moving faster than it actually is. But yes, so we're just going to record that. So same thing as with the aluminium.
Again, so what's being recorded is the horizontal and vertical force. These data files will be provided to you. They'll be available in Sakai. So this time we see our chip forming, again making a curl, but its curl's a little bit of a different configuration, and it started to curl over earlier. And in fact, now we see that the chip itself broke and it's making a second chip now. So we've now made a discontinuous chip. We're still only about halfway across our piece of material. Due to the very slow rate at which this lab runs, we're going to show you the first set of feed rates, and then we'll actually not make you sit through all the video, so because this would drag on for about 45 minutes. So we'll see the first feed rate on all three materials. Again, right now we're still on the brass.
We've had like 4 different chips now.
Yeah, so the brass has this tendency for the chips to break up. We'll take a sample chip from this collection of chips and do our chip thickness with this after we're across this piece of material.
Further than the rest. It's broken off again.
So getting these chips into the micrometer is kind of a bit of a tricky business because they're so curled up. So we're using some tweezers here, and Jesse's carefully inserting it into the jaws of the micrometer and getting a reading. As you're filling this out on your data sheet, keep in mind that these are all for feed rate of 0.6. So you're filling in on the first chip we did, that was your first block off to the upper right. And now you're going down to brass for table feed of 0.6. So our chip thickness in this case is
0.01675.
okay. So that was our brass chip thickness for 0.6 table feed.
So the last piece we're going to work with is copper. So same feed rate 0.6. Jesse, start over there. And we're off. Although you probably cannot see it. Or you might, depending. Tweezers?
On the copper, we're getting a much straighter chip than we were with the other two materials. You can see it kind of building up at the base at the point of that cutting tool. This is what's happening when you look at lab 4 and the machine is spinning a lot faster and moving at a faster speed. You still have this same process going on, but it would be happening so quickly that you wouldn't be able to see it, which is why we've simulated it here in this slow motion kind of format. The forces that build up at the point of that tool are the same regardless of whether it's a turning process or a milling process. In a turning process, you typically only have one point on your cutting tool, whereas in milling, you usually have more than just one point acting. In this case, we're actually on a milling machine. The milling machine we're using is called a Series 1. Pretty typical in a manufacturing company to have one of these kicking around. Technology's existed for many, many decades, but still very useful for any manual operations you need to do. So if you hear a Bridgeport Series 1, very, very common machine, and that's essentially what we're using today. So we're using a milling machine to simulate a turning operation. So we can see that this chip has come out much, much straighter. Should be a little bit easier to measure. And again, this is our copper at 0.6 table feed rate. We're approaching the end of the piece of material, so Dominique's going to try to catch this chip so that we don't lose it. So this is for copper for feed rate of 0.6. Our chip thickness is
0.02215.
Now we're moving on to our new table feed rate of 1.5, but the first thing we have to do, we've reset the machine back to the beginning of the pieces of material. We're going to need to reset our depth of cut, so Dominique is going to move us 4 tick marks to set our 4,000th depth of cut. And now we need to adjust the machine so that we can have our feed rate of 1.5.
Okay, so 1.5 is all the way up here. So first things first, we want to bring this part up here. And then this is already at the slower speed, so we're already at 1.5 there.
Okay, so now we're going to start cutting again at the beginning of our material. because this runs so slowly, we're not going to make you watch all of this video. We're just going to show you the start of our aluminum, and then we'll magically come back with our 3 thickness measurements. So here we go. We're starting our second set of feed rates at 1.5 on our piece of aluminum. And you will magically fast forward to all 3 pieces of material being done.
But if you do notice, it's going a tad faster than the first one.
We are still moving really, really slowly. So we've more than doubled our feed rate. If we look over here at the actual part moving, you can see it's not moving particularly fast. Nowhere near what you'd be doing in an actual cutting operation. But again, we've slowed it down just so we can get a good view of our chip thickness and a good analysis of our force measurements. Again, we'll talk about this in lecture with what's going on at the point of that tool, and we'll actually get to do some calculations with real-world data. All right, so we'll be back shortly with all 3 pieces magically finished. Okay, so we've completed the feed rate of 1.5. Here are your values. For aluminum, your chip thickness is 0.02025. For brass, it's 0.03012. Sorry. I'll read that again for brass, 0.03015. And for copper, 0.04000. Now Dominique is going to show us resetting the machine and adjusting our feed rate to our final value of 2.3.
Okay, so just to make the resetting go faster, I just generally put it on the highest speed and then just let it go. Okay, I need to adjust the timer. Okay, so to change 2.3. Okay, so to change the speed, it's best to just always put it at the slowest mode, so up top for this handle, because if you try to move it when it's at the fastest, it's just not going to. So we are going for 2.3. 2.3 is the second number down here, so we want to bring it over on this side, and then you put this on medium. So the slow up here, medium, and fast. So we want to put it on medium because it's the second speed right here. And then we go and adjust our depth of cut again. So once again, we're just moving it down 4 tick marks. So 1, 2, 3, 4. Yeah, and we're all set to go. So just to start off, just so that you see how fast it goes compared to the others. And
so now we have our feed rate of 2.3, and we can see how quickly this is moving. And notice on our screen here, we have a pretty straight chip coming with our piece of aluminum. And here's what this is looking like in real time rather than amplified by the video camera. About 2/3 of the way across, our chip is now finally starting to curl. Alright, so we're going to capture these chips and we're going to run this for all 3 materials, and we'll be back to you shortly with our chip thickness readings. Okay, so now we have completed all 3 trials on all 3 materials. Here are your chip thicknesses for the 2.3 feed. For aluminum, the chip thickness is 0.01730. For brass, your chip thickness is 0.01350. And for copper is 0.03245. What you're seeing on your screen here is one of the files that will be available to you in Sakai. There's a total of 9 files available there, one for each of the materials and feeds. What these give you are the horizontal and vertical force as measured as we conducted the experiment. To get your actual horizontal and vertical force number, you're going to want to take an average of the appropriate column. When you're doing that, make sure you cut off any data that seems to be false at the beginning and the ending of the run, as the machine may not have been contacting the material. So you can do that by looking at it graphically, if you graph all of these as points on a line, or you can probably just look at the columns of numbers and know what you should truncate. So again, you're going to want to take an average to get your average force. Your horizontal force is what's shown under the column for channel 1, and your vertical force is shown on channel 0. Keep in mind that that's backwards to the orientation that you have on your data sheet as you're calculating and recording that information. All right, so this concludes the video portion of Lab 6. For further information on how to complete the lab, refer back to your lab document and information in Sakai.